the system is released from rest, if the blocks are accelerating, find the acceleration acting on the two masses. So what we've got is we've got some weird pulley assembly system here, connected by two pulleys here, and we're asked to find out whether these blocks are accelerating downhill, and if they are, what is the acceleration of this one, and also what's the acceleration of this one. And even though it's not mentioned here, we're meant to assume that the masses of the pulleys and the cables are zero, just for simplicity's sake. So in order to figure out this question, first we need to find out whether the blocks are actually accelerating or not. And that involves using this formula right here, mu Sn, right? Mu S. And in order to properly do this, what we need to do is we need to analyze this block using a free body diagram and find out the corresponding equations. So let's just draw that right now. Let's say we've got, I'm just going to redraw our slope right there. We've got our block lying on it, like so. And we know a block has 60 kilograms and it's sliding, or it could be sliding, we don't know yet. 60 kilograms just here. 60 kilograms. And if we wanted to draw all the forces acting on this block, well, one would be acting through the center of mass, going straight down, that's our gravity, mg, or in this case, 60g. We've got a normal force, which is going to be acting perpendicular to the slope, because the normal force is being applied from the slope, so that's going to be n. And we're also going to have a tension due to the cable, which is going to try and pull it up with the tension, or a force, T. And depending on which way the block has a tendency to want to move, the friction force will either be in this direction, or it'll be in this direction, and we need to account for both cases. So let's first consider the case that the sum of all external forces acting on it are trying to move it up the hill, which implies that the friction force will be down the hill to try and resist movement, right? And if we're trying to figure out whether this block is going to be stationary, we need to concern ourselves with the friction force mu Sn. Right, I did a video on why this, well, I did a video describing roughly how to use mu Sn. This is just going to be a particular example of using it in a more sophisticated example. So, first of all, let's try and analyze this using sum of forces in the horizontal and vertical direction. So we know that the sum of forces in the vertical direction are going to be equal to 0. We know this because regardless of whether the block's sliding up or down the hill, the block will not be accelerating into or out of the ground, right? I mean, there's going to be the forces vertically are going to equal to the up. The forces directly up are going to be equal to the forces directly down, which implies that n is going to be equal to your component of gravity, which is going down in the negative y direction. And in order to do that, we need to use simple trig to figure out what is the component of gravity in the vertical direction. Well, we know that this angle right here is 30, which means we know that this angle here is 30, which means that we know the component of gravity in the vertical direction is simply just going to be 60g cosine 30, which means that n is going to be equal to 60g cosine 30, right? If the sum of forces is equal to 0, that means the sum of forces going up are going to be equal to the sum of forces going down, which means that this equation must be held at all times. Now, if we're interested in finding an upper limit for which the block won't move, what we need to do is we need to establish a case where the sum of forces in the vertical direction are going to be equal to 0 too, right? This is implying that the block is not going to be accelerating. If the sum of forces in the horizontal direction are equal to 0, that means the block isn't going to be moving, which means that the friction coefficient is going to be just enough to stop the block from moving. So, in this particular case, T, the forces acting up the hill, are going to be equal to all the forces acting down the hill, which means T is going to be equal to 60g sine theta, right, because that's the component of gravity in the horizontal direction, plus mu Sn. And in this case, we just figured out what n was before, so that's just going to be 60g sine theta, or sine 30 in this case, plus 60g mu s cos 30. I hope my handwriting's not too bad. Alright, but let me really explore what this actually means. This is an upper limit for which t must be such that the block doesn't move. right? If T was any greater than this, that means that the tension you're applying on the block is just enough to overcome both the friction and the force due to gravity, right? If T was any less than this, but still greater than 0, then the block would not move, right? So in other words, we can say and this is just writing an inequality here, if T is greater than, well, this, that means the block will slide up the hill. It's enough to overcome the gravity and the resistance force being applied on it. So if T is greater than this beast, which I've written here, 60g sine 30 plus 60g mu s cos 30, then the block will be sliding up the hill. Right? And I really want to establish how I went from here to here. This right here is establishing the bare minimum, the very maximum for which T must be such that the block doesn't move, which means that if T was any greater than that, it would be enough to overcome it and start moving uphill, right? Okay, but that's not every condition we've thought about. We know that, like I said before, that the friction force could be in the opposite direction, right? So let me just copy this rather than having me redraw it over again, and I'm just going to paste it below, right here. Just saves me drawing it out again. Ta-da! All right, so let me just isolate this little inequality off right here. All right. So we've considered the case where the block has a tendency to try and move to the right. But what if the block has a tendency to try and move to the left? And what I mean by tendency is there's a force acting left, or acting down the slope, which implies that the friction force will be acting towards the right. So in this particular case, we know, just like before, the sum of forces in the y direction are going to be equal to 0, which implies that n, just like before, is going to be mg, or in this case 60g, what did I say, what was it, cos 30? Yeah, cos 30. And we know that a lower limit for which T needs to be in order for the block not to move is the sum of forces in the x direction must be equal to 0. This is for the block not to move. This is just our two extreme cases, and that means that T plus mu sn, or I'll just write mu s 60g cosine 30, is going to be equal to 60g sine 30, right? The sum of forces up the hill is going to be equal to the sum of forces down the hill, in the case that the block isn't moving, 60g sine 30. I should also write a 30 here, just there, so you guys know. Alright, so, but once again, let me explore what this formula even means. This is the formula which, this describes the value of T, or the tension in the cable, which needs to be satisfied so the block just doesn't move downhill, right? In fact, if T was any less than this, in other words, if T was pushing any further down the hill, that means the block would be trying to slide, would actually succeed in sliding down the hill. So let me just make T the subject of this equation I've got right here. If T is equal to 60g sine 30 minus 60g mu s cos 30, this is what needs to be satisfied in order for the block not to move. But if T was any less than this, i.e., if there was any more force trying to push this block down the slope, then the block would the block would not have enough to keep it from being stationary. In other words, the sum of forces in down the hill would exceed the resistance due to friction, and the block would succeed in rolling down the hill. So let me write another inequality here. So if T is any less than this, is any less than 60g sine 30 minus 60g mu s cos 30, that means that the block will be sliding downhill, right? In other words, I could have kept, well, I mean, I've already explained this a dozen times, but let me just try and hammer it down one more time, because it's a very important thing to understand. If this t value represents a lower limit for which t must be such that the block doesn't move, but if it gets any lower than that, in other words, if there's any more of t pushing it down the slope, then it will actually break that threshold, and it will start sliding down the hill. So in order to determine whether this block is going to be stationary, we just need to check which one of these inequalities it satisfies, and if it doesn't satisfy any of them, that means it's not moving, right? If it's not sliding up the hill, or if it's not sliding down the hill, that means it's not moving. There's no other options left. But in order to do this, we now need to figure out what t is. Well, remember, we're considering the case where the block is stationary. So in this case, we need to figure out t by now analyzing this bit just here. And what I'm going to do is I'm just going to take a small slice of this. I'm just going to take a small cut of that, and I'm going to analyze this as a free body diagram. So bear with me. I think you'll understand where I'm going with this. But I'm just going to redraw this, and I'm going to have sliced these two cables and replaced them with forces. And we know that there's a cable down here too. And we know that this cable's tension right here will have a magnitude of 20G, right? Because that's the force acting on the cable, this cable right here. But we know that this cable here is going to have a tension of T, and this cable is going to have a tension of T as well, and it's going to be facing upwards, mainly so it can satisfy your intuition. But I mean, think about it logically. I mean, if this was directed downwards, that would imply that the spring is just going to become limp and float downwards, which doesn't really make sense. But also, the cables are going to have equal tension because all throughout this particular point, each part of the cable has the same tension acting on it, because the springs are also massless. I won't go into too much detail into why that's the case, but for now, this is the case. This is what needs to be considered when we're considering whether the block is going to be stationary or not. And this is working with the assumption that the block is stationary, so you're not going to have a net acceleration acting down. Anyway, I don't want to confuse you guys too much with that. Later on in this question, I'm going to approach this. But for now, we're considering the case where this pulley system, this particular part just here, is not moving, right? We're working with the assumption that the block is stationary, which implies that the sum of forces is going to be equal to 0, which implies that 2t is going to be equal to 20g. Right? I mean, sum of forces up is going to be sum of forces down, which implies that t is actually going to be equal to 10g. T is going to be equal to 10g right here. Oh, I really screwed that up. That's 10g right there. 10g. I hope you guys can understand that. Okay, so now we've got t, and we know every single value of this term in here. We can just simply plug in each of these values to determine which one of these inequalities are satisfied, if any of them are. So let's first check whether this inequality is satisfied. Well, 10g is just going to be 98.1 newtons. And we're checking whether that's going to be greater than 60 times 9.81 times by sine 30 plus 60 times 9.81 times mu s, which in our case is 0.25, times by cosine 30. And that becomes 421.7 newtons. Is this inequality satisfied? Absolutely not. There's not a chance that 98 is greater than 420, right? So this inequality is not satisfied. All that means now is that the block is not moving to the right. That's what that means. Block not moving. I'll just put not moving to the right. So now we need to check whether the second inequality is satisfied. If it is, that means the block is moving to the left. If not, that means the block isn't moving downwards, which means the block is stationary. So we know that t, which is 10g, is just going to be 98.1, just like before. And we're checking whether that's going to be less than 60 times 9.81 times by sine 30 minus 60 times 9.81 times 0.25 times cosine of 30, which is going to be equal to 166.8. Actually, it should be 0.9, just to be accurate to one decimal place. And is this inequality satisfied? I think it is. Well, 98 is definitely less than 166, so this equality is satisfied, which implies that the block is moving down the hill. So block is moving down the hill, right? So this may be a laborious process to do every time, but I think you'll get faster and faster at it when you practice. But this is also a really crucial step, because you can't assume that the block is moving down the hill or up the hill to begin with. You have to figure out whether it's going to be stationary or not. And the block would have been stationary if none of these inequalities were satisfied. Anyway, so we're halfway through the problem. Let me just, and we've done the most work. From here on, it gets a little bit less tricky. But now that we know the block's moving downhill, we can actually redraw this particular free body diagram, knowing that because the block is moving downhill, you're going to have a resistance force acting uphill at all times. So let's first pull all the information we know about this particular block just here. Let me just copy this over again, saves me from drawing it. Took me forever to draw that. Let me scroll down just here. Alright. So this is our assembly. We know the block is going to be moving downhill. And we also know it's going to be moving downhill with an acceleration of a. And I'll just call this ax. And we can't assume that this block is going to be accelerating upwards at the same rate. In fact, we'll need to calculate that. But we'll just call this acceleration downwards. We'll say the block of this 20 kilogram blocks is just going to move downwards at an acceleration of ay. And in order to equate ay and ax, here's an interesting little trick. So what I'm going to do is I'm just going to label this distance from this midpoint of the pulley here onwards till it touches this block as x. And I'll label this point from here to here as y. You'll see why I'm doing this. This is a little interesting trick to equate ax and ay. But let's figure out how this is going. So if we were just purely out of interest finding out what the length of our cable is, we can say our length of our cable is going to be x, right? It's going to be this length plus whatever this length is, which is going to be, let's see, it'll be 2 pi r, right? We're assuming that this pulley is a radius of r. 2 pi r divided by 4 plus y plus, and then we're going to plus this part of the cable, which is going to be 2 pi, I'll draw little r to denote this radius of the smaller pulley, divided by 2 plus y again, because it goes back up here of the same magnitude y. Well, first of all, we need to establish that x is actually a function of time, and y is a function of time too, right? Considering that this block is actually moving downhill, and we know it is now, this distance x will change depending on the value of time. Likewise, this distance y will change as a value of time as well. So they're not constants. These are actually functions of time right here. So if we were interested in differentiating the left-hand side and the right-hand side with respect to time, that means that 0, because L is a constant, is going to be equal to dx dt plus 0, because this is a constant, the radius of the pulley remains constant, plus dy dt plus 0 plus dy dt. Right? When you differentiate a constant, they just turn to 0. And because the length of the total cable is going to be constant, that means dl dt is going to be equal to 0 too. Well, we can now simplify this expression a little bit more, and we can say, well, dy dt, just by, I won't bring you through the laborious algebra, but dy dt is actually just going to be equal to, what would it be? It would be negative a half dx dt. That's just grouping dy dt's and dividing by 2. Alright, well, if we were to differentiate one more time with respect to time, that would imply that d squared y dt squared is going to be equal to minus a half d squared x dt squared, dt squared. and this is a really interesting formula right here. This is really interesting because notice that our change in y with respect to time is also going to be equal to our acceleration of our block with respect to time too. Sorry, our double derivative of y with respect to time is going to be equal to our acceleration of time, right? The rate at which this part of the pulley is going to be moving down is going to be equal to the rate at which this block is going to be moving down as well. So d squared y dt is going to be actually equal to ay. Likewise, d squared x dt squared is going to be equal to your acceleration of your block moving down the hill, right? Because if this cable's moving downwards at a certain acceleration, that means this block is also going to be moving downwards at that same acceleration. So d squared x dt is going to be equal to ax. So this is going to be one formula which we're going to use later on. Alright, we're almost there. We just need to analyze, once again, this block in kinetic friction, and then plug in everything we know, and we'll get our answer. So in order to do that, let me just draw another free body diagram of our block on the slope. I know this is taking a while, fellas, but we're almost there. So we've got our block like we did before, and we know it's going to be sliding downhill. We know that. We calculated it earlier. Which means that you're going to have some net acceleration ay of this block. Or did I denote that as ay or ax? Let me find out. Sorry, I denoted it as ax. You're going to have some net acceleration of this block ax. And the forces acting on this block are going to be the exact same as it was before. It's going to have a force due to gravity right here. It's going to have a normal force just here. It's going to have a tension acting on it. And not only that, but you know this time that the force due to resistance or static friction is going to be, kinetic friction this time is going to be UKN, right? Because the block is moving, we use our kinetic friction formula this time. Alright, so now we can analyze this block using our dynamics equation, and we know that the sum of forces in the horizontal direction, are going to be equal to our mass of our block, 60, times by our net acceleration of our block, ax. Right? Notice how it's not 0 this time, because the block is not static. So that implies that 60 ax is going to be equal to, well, the force is acting down the slope, it's just going to be mg, mg sine theta, I believe it was. Let me just scroll up here. It would be mg sine 30, yep. mg sine 30. Alright, that's the component of gravity acting down the hill, plus any other forces acting down the hill? No, that's it. So we're going to subtract that from all the forces acting up the hill, which is going to be T, and then subtract that from another force acting up the hill, which is going to be mu kn. And we know that n, just like it was before, mu kn is just going to be 60g cosine of 30. I won't bother writing out fy is equal to 0. We already know. We've done it enough times to know that n is just this bit just here. That's n. So now this is going to be one equation right here. Let's grab another equation, and then we'll use simultaneous equations to solve this entire beast. So now in order to solve this, we're still left with a pesky little t out here, right? When we don't know what the value of our tension is because the block is moving now. We can't assume that the block is stationary, well, because we know it's not. So if we were to draw a little pulley system for our 20 kilogram block like we did below, we know that there's going to be 2 strings of equal tension on it. And we know that the block is also going to have a downwards force acting on it of 20g. 20g. But we also know that the block has a net acceleration now, and I have to find the acceleration downwards as being positive, so this is going to be ay, which implies that if I were to do the sum of forces in the y direction, sum of forces vertically is going to be equal to 20 times your acceleration, your net acceleration, which is ay, right? So this equation right here is all connected to this. In fact, let me write it right below so I don't confuse you. So our net acceleration, the sum of forces in our vertical direction, and our vertical, I'll denote V as vertical, is going to be equal to your mass of your block. So that's 20 in this case, times by your acceleration, your net acceleration of your block, AY. Oh, this cough is killing me. Alright, so the sum of forces in your vertical direction are going to be equal to 20G subtracted from 2T, right? And that's going to be equal to 20 AY. Alright, we're almost there. So that's going to be another formula just here. So we've got 3 formulas and 3 unknowns. We've got 3 unknowns, AY, AX, and T, and we've got 3 equations. If we manage to plug them all in, we'll be able to solve this beast. So let's try and do that real quick. Let's first try and eliminate T, because that seems to be the biggest annoyance of us right now, even though you could eliminate whatever one you like first. What I'm going to do is I'm going to substitute T from this one here. I'll call this equation 2, I'll call this equation 3, and I'll call this equation 1. And what I'm going to do is I'm going to sub 3 in 2. I'm going to sub 3 in 2. Well, this is, I'll kind of speed through the algebra here, but what I'm going to do is I'm going to make T the subject of this equation and sub it in there. So we know that our equation 2 will now become 60 AX is equal to mg sine 30 excuse me, mg sine 30 minus t, which, and we know t is going to be equal to this, whatever this is when t is the subject. It's going to be equal to 10, let's see, it'll be t over there divided by 2. It's going to be 10g minus 10ay minus mu s 60g cosine 30. Oh wow, I feel like I'm still at a fly right now. Bear with me. Alright, so that's one simplified equation right now. But we still can't solve it completely because we've got 2 variables, ay and ax. And which means that what I'm going to do now is I'm just going to substitute ay in there, and ay in our new equation, and solve it. So I know ay is going to be minus a half ax. So this is going to be equal to mg sine 30 minus 10g plus 10 ay, which we know was minus a half ax, minus a half ax minus mu 60g cosine 30. And what I'm going to do is I'm going to bring all ax's over to the left hand side. I'm going to factorize out of ax, and that'll become 60 ax plus, see what's 10 times a half, it's going to be 5 ax is going to be equal to mg sine 30 minus 10g let's see, it's over, so it's going to be minus mu s 60g cosine 30. And what I'm going to do is I'm just going to do this in one step. I'm going to 60 ax plus 5x is 65 ax. I'm going to divide all this by 65, and I'm going to be left with ax is going to be equal to, and I'll just plug it into my calculator, 1 on 65 times by m, which in this case, well, let's see, what is this m? I should have really stuck to the 60-20 sign because m could be anything. 60 sine 30, so this denotes our 60 kilogram mass. Sorry for confusing you. That's 60 right here. That's 60. That's 60. So that's going to be 1 on 65 times 60 times 9.81 times by sine 30 minus 10g minus mu k, which is 0.2, times by 60 times 9.81 times by cosine 30, which is going to be equal to 1.4500 meters per second squared. AX is going to be equal to this, and we've denoted AX, remember, as being downhill because we knew it was traveling downhill. So that's going to be our acceleration of our 60 kilogram block down the hill. So this is our acceleration of our 60 kilogram block down the hill. It's traveling at 1.45 meters per second squared down the hill. Now it becomes a matter of finding out what the acceleration of our block was, our 20 kilogram block was. Well, we know from our previous equation, equation 1, that ay was equal to minus a half ax. Ay is going to be equal to minus a half ax, which implies that ay is going to be equal, times it by minus 0.5, is going to be equal to negative 0.725 meters per second squared, and that was also directly downwards, right? Because I denoted ay as being downwards, right? But we know that a negative acceleration downwards is the same as a positive acceleration going upwards. So in other words, we can say that ay, or our acceleration of our 20 kilogram block, I'll just denote that as a20, our acceleration of our 20 kilogram block, which I'll denote as a20, is going to be equal to 0.725 meters per second squared directly upwards. Alright, I feel like I'm dying here. Alright, so let me just explain what this means. So you've got, in other words, what I'm saying is, in our original problem right here, our block right here, this 60 kilogram block, is going to be accelerating downwards at 1.45 meters per second squared. And our block here, intuition tells us that it'll be traveling uphill, but we know that it's going to be traveling uphill at half the magnitude, which is going to be 0.725 meters per second squared up. And that's our problem.